All right, I'm going to look at practice exam 1. This is, it's in the Barron's book. I believe it's page 472. Okay, slightly off. All right, so multiple choice. First question, following is a histogram of home sale prices in thousands of dollars in one community. Which of the following conclusions is most correct? All right, so read through them. Median price is $125,000. Mean price is $125,000. More homes sold between $100,000 and $125,000 than for over $125,000. That's something we could easily verify, I think. 10,000 is a reasonable estimate of the standard deviation of selling prices. And 1.5 times 10 to the ninth power is a reasonable estimate of the variance in selling prices. All right, so there's a lot of funkiness on this one, but if we assume that the total amount that's covered here is going to be 100% of whatever the total number of home sale prices is, then we can kind of break up our graph and just kind of see where that gets us. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each little block here amounts to a 10%, assuming that the scale is reasonable, 10% of the listing of home sale prices. All right, just for benefit, I'll put this in here. Not anything that you'd have to mark up on the exam. All right, so when it comes to something like the median price would have to be, and again, just be careful about the instructions. It says most correct. The median price would be the middle price, and let's see, that would be at the 50% mark. So 10, 20, 30, 40, 50. The median is going to be somewhere in this interval. Right? We don't know precisely where, but it's not 125,000, because if it were, and this one wouldn't be there. All right, we'd have 50% below it, 50% above it, so it would have to be something maybe like that in order for that to be the median. All right, so that's not the case, so we'll dismiss that one. Yeah, so the mean would be somewhere in this neighborhood. As we look at that as kind of like the balance point. All right, I think the Barron's book calls it the center of gravity, but it's kind of like the fulcrum, right? So if you were trying to balance this, where would you put the mean? And probably somewhere in that same neighborhood. It's roughly, it's I wouldn't say it's symmetric, but it has a little bit of symmetry to it. So the median is going to be somewhere in this interval here. So I can't definitively say that it was 125,000. More homes sold for between 100,000 and 125 than for over 125. We got 30% in the 100 to 125, over 125, so that'd be all of this would be about, it looks like 40%. All right, so that's not a true statement. In terms of the standard deviation, so we're going down the road here of process of elimination. When they tell us the standard deviation is 10,000, then they tell us the variance is 1.5 times 10 to the ninth. That's the standard deviation squared. So 1.5 with 8 zeros after it. 360, yeah. If I want the standard deviation, I'm going to take the square root of that. All right. So the square root of 1.5, put another comma there. 1, 2, 3, 4, 5, 6, 7, 8. All right. So 30, like about, I'll say standard deviation is in the neighborhood of like 39,000. Would don't have to be precise here. It's multiple choice. We're just trying to find the one that's the best option. But if we assume that the mean is somewhere in this neighborhood, where I have it marked in purple, and then we go out 10 unit or $10,000 in each direction, that's going to get us kind of like here to here for one standard deviation. Then let's say 125, 135. So somewhere around here for 2 standard deviations, around here for -2 standard deviations. It looks like we're going to get out to over 3 standard deviations before we've accounted for a substantial part. Sorry, that should be a 3. Substantial part of the data. And generally, even if it's not a normal distribution, you shouldn't be looking at 10 to 20% of the values beyond 3 standard deviations away from the mean. Right? That's a whole lot of data points that would be falling into the category of potentially being outliers, and that does not seem to be the case. So the one that seems most correct, I would eliminate this one. I would have to go with E, because it does seem to be more widely spread out than what the 10,000 seems to indicate. And this one was just not true, C. And these two we couldn't really confirm. It was a definitive statement, so I'd have to settle for E on this one. All right. Number 2, which of the following is most useful in establishing a cause and effect relationship? That would be a controlled experiment. Didn't say controlled, but we'll take it. It's got to be an experiment. Complete census is not going to give us cause and effect. All right, we have to establish a relationship between 2 variables, and the only way to do that is to control for any lurking variables, factors that might exist. All right, and that would only take place in an experiment. Least squares regression line showing high correlation. That could show a correlation, but that doesn't mean that there's a causal effect. Simple random sample, for the same reason it's not A. And a well-designed, well-conducted survey using some sort of randomization, that's great, but it still doesn't establish the cause and effect by controlling for any lurking variables and imposing a treatment. Right? So it's got to be an experiment. All right, the average yearly snowfall, so number 3, in a city is 55 inches. What is a standard deviation if 15% of the years have snowfalls over or above 60 inches? Assume yearly snowfalls are normally distributed. All right, average, so that gives me a mean. Standard deviation, so we know that information. So we'll say mu is equal to 55. Sigma is equal to, it's asking what sigma is, so we'll hang on to that. 15% of the snowfalls have averages, or years have snowfalls above 60 inches, sorry. So it's telling us that the probability that X is going to be, so some random variable X is going to be above 60 inches is equal to 0.15. All right, so I would use my inverse norm, because I'm given the area. Sorry, that's a poor question mark there. It did say normal distribution, so inverse norm distributions, normal. I could pop in, so in this case I would do 0 and 1, because I don't know what the standard deviation is. So it would give me a particular value as a return. The problem is I need to know what the standard deviation here is, so it's asking for a little bit of a twist. Above 60 inches, so if I'm looking at a normal curve here, it's saying that 15% is on the eastern side here. So I'll grab a z-score from this, and then I'll use my z equals x minus mu over sigma. So I'll put in my percent as a decimal. The inverse norm uses area to the left, so 0.85. So 0.8501 gives me a z-score of roughly 0.0364. So again, I put 0.85, comma 0, comma 1, treated as standard normal. Let me just move some things around here. Maybe shrink it down a little bit. All right, so I'm going to compute, knowing that my z-score is 1.0364. My particular value set above 60, so that's my x, minus the mean of 55, divided by my unknown sigma. So sigma, use a little cross multiplication magic. I'm going to take 5 and divide it by 1.0364. Going to grab the closest one, which is, so I got about, I use a rounded value, but I got about 4.824. All right, so about 4.824. The closest one to that is A. All right, so if I use the more precise decimal value, so 5 divided by, then grab this one, maybe it would have got me a little closer. Nah, I went out enough digits, but it's possible that they're using the z-score tables. We use a calculator, so we just grab the one that's closest to it. All right, number 4, to determine the average cost of running for a congressional seat, a simple random sample of 50 politicians is chosen and the politicians' records examined. Cost figures show a mean of 125,000 with a standard deviation of 32,000. Which of the following is the best interpretation of a 90% confidence interval for the average cost for running for office? All right, so we tend to say, I mean, kind of sort of rehearse this in class. With 90% confidence, we can say that the true population whatever is between this and that. We're looking for the one that's closest to that. These are just straight statements about percentages, so those are almost never right. We are 90%, so I'm looking at C, confident that politicians running for a congressional seat spend between those two numbers. We are, in D, we are 90% confident the politicians run for congressional seats spend a mean dollar amount. That's what a confidence interval would tell us. A population mean, population proportion, something like that. That's the key word that's missing, so it's not C, it's going to be D. And there was an E that I probably should have evaluated. I don't know why it didn't even occur to me. Let's see about this one. We are 90% confident that in the chosen sample, well, right there, we already know what's happening in the chosen sample. We want to know how that projects to the population. So E would be out. All right. Number 5, in one study on the effect of eating meat products has on weight level. A simple random sample of 500 subjects who admitted to eating meat at least once a day had their weights compared with those of an independent simple random sample of 500 people who claimed to be vegetarians. In the second study, an SRS of 500 subjects were served at least one meat meal per day for 6 months. I'll just underline served there. All right, this one is admitted. For 6 months, while an independent simple random sample of others were chosen to receive a strictly vegetarian diet for 6 months, and weights compared after 6 months. So we're looking at individuals who admitted to doing something, who claimed to be something, all right? That seems more like a survey. In the second one, they were served and they received either one meal per day, one meat meal, and the other group got a strictly vegetarian diet for 6 months. That's a set of treatments, all right? So in the first study, we're looking at something involving surveys, so that would be observational. So the first one is not controlled experiment, meaning both are not controlled experiments. The first study is observational, while the second one is a controlled experiment. That seems to be the correct answer. Both are observational. No, because there is a treatment in the second study. Each study is part controlled and part observation. That's not a thing. All right. Number 6. Looks like a probability question here. A plumbing contractor obtains 60% over boiler circulators from a company whose defect rate is 0.005, and the rest from a company whose defect rate is 0.010. If a circulator is defective, what is the probability it came from the first company? All right. So it's a conditional probability question. So we're looking for the probability that it's coming from the first company if it's defective. All right. So I need a couple of things. My formula sheet is pretty useful when it comes to stuff like this. We have probability, I'll just jot it down here, probability of A given B is equal to the probability of A and B over the probability of B. All right, so that's the rule we're working off of. Actually, I'm going to swap these. So I'm looking for the probability that I'm from the first company and defective versus the probability, or divided by the probability of being defective. All right, so we would need the law of total probability here to get us the probability of being defective. All right, so, and for the simple multiplication, so we're looking at an AND case, we can just take the two values, the 0.6 and the 0.005, I think it was. Yeah, because if you're in the company, so the first company here is your 60%. The second company, so we could say first, and second we can say initial, and then other, however we want to do it. But I'm going to take my 0.6 and multiply it by the probability that we're going to be defective. And so in the first company, and a defective value. If it's coming from the other company, sorry, my notation here, my handwriting, everything. I'll just resize a little bit. My total probability is going to be really any instance in which there could be a defective item. All right? Maybe it was from the first company and defective. Maybe it was from the second company, that's the other 40%, and defective. All right, so I could run these numbers. That's not what I want to do. 0.6 times 0.005 divided by 0.6 times 0.005 plus 0.4 times 0.010. And we get about 0.429. All right. So with these conditional probability questions, you're really looking, the key to everything is the bottom. This is the law of total probabilities. Law of total probability. All right. So we want to use that as our denominator because that gives us any instance in which a item could be defective. All right, number 7, looks like type 1, type 2 error kind of situation here. Kidney dialysis center periodically checks a sample of its equipment and performs a major recalibration if readings are sufficiently off target. All right. Similarly, a fabric factory periodically checks the sizes of towels coming off of an assembly line and halts production if measurements are sufficiently off target. So in both cases, there's some sort of recalibration going on. It's just one is a little more, I guess, trivial than the other. Although I guess people who work in a fabric factory maybe won't think so. It's just kind of odd to compare kidney dialysis to towels. So, it's just a personal thought. And halts production if measurements are sufficiently off target. In both situations, we have a null hypothesis that the equipment is performing satisfactorily. For each situation, which is the more more serious concern, a type 1 or a type 2 error, right? So a type 1 is mistakenly reject the null. All right, and we think about that in the context. The kidney dialysis center is going to periodically check its equipment, and if the readings are off target or whatever it is, whatever it is they're measuring, particular to the readings, if they're off target, they'll do a recalibration. So the null hypothesis here is that they're performing satisfactorily. So if I made a type 1 error on a kidney dialysis machine and said, you know what, I think it's out of whack, we better recalibrate it. If I'm wrong, what's the big deal? We recalibrated, we updated, fixed something that maybe didn't need to be fixed, but people's lives are at stake. Maybe that's why they chose this question, right? So it would be really bad if we had a type 2 error when dealing with the kidney dialysis machine, because a type 2 error is mistakenly, in both cases mistakenly, reject the alternative, all right? Or I prefer to think of it as keep the null, all right? So if it turned out that there was something wrong with the dialysis machine and I mistakenly rejected the alternative, meaning I kept the null, I'd be saying, I think the machine is fine. And that would be a problem if it's not fine. All right. So it's going to be really bad if there's a type 1 error, or type 2 error on the dialysis machine. So let's get rid of these. For now evaluating the towels, I mean, I don't want to say like big deal, who cares? But if I say that the machine is performing satisfactorily as my null hypothesis, if I reject that mistakenly, so making it a type 1 error, then I'm looking at saying that it's not performing satisfactorily, and it's checking the sizes of the towels coming off the assembly line, and then it halts production if measurements are sufficiently off target. All right, so the machines are going to stop if we say that there's some calibration that needs to be made, but again, it's not as big of a deal as doing it for the dialysis machine. All right, so I would say in this case that it's C, because if there's a type 1 error, all right, so I'm mistakenly rejecting the null hypothesis, all right, then what I would be saying is I don't think the machines are performing satisfactorily. So then we stop production, we fix the whatever needs to be fixed, and then everything gets started up again. All right, so in this case, type 1 error on the case of the towel manufacturer, because at least in that case we halt production and we see what's going on. All right, it's really just a matter of knowing what your definition is for a type 1 and type 2. If you're good with that, then you can generally reason your way through these kind of problems. Number 8, sampling distribution. A coin is weighed so that the probability of heads is, weighted. So the probability of heads is 0.75. The coin is tossed 10 times and the number of heads is noted. The procedure is repeated a total of 50 times and the number of heads is recorded each time. All right. What kind of distribution is being simulated? So if we know our distributions, we have sampling distributions, which are your central limit theorem. We have chi-square distributions. We have normal distributions. We have binomial distributions. So any one of those could be relevant. If you know your conditions for binomial, for example, whenever I'm asked to determine what kind of distribution is most appropriate, I go down my list, fixed number of trials, fixed probability, independent events, 2 outcomes. All right. And if that works, then I'm going with binomial distribution. All right. So the coin is weighted so that the probability of heads is 0.75. It doesn't seem like that's ever going to change. So fixed probability. Independent events, I think we can assume that because you're flipping a coin, you get heads one time. It doesn't impact the probability of getting heads another time. Speaking of heads and tails, 2 outcomes. So then it's just a question of how many trials we have. The coin is tossed 10 times and the number of heads is noted. All right. Now the procedure itself is repeated 50 times, but that doesn't mean we flip the coin 50 times. And in fact, you would say we flipped the coin, 500 times, right? Because 10 times per trial, the repeated part is a replication, right? So we did not flip the coin 50 times, we flipped it 10 times, so D would be the most appropriate here. The sampling distributions for A and B are talking about sample proportions or a sample mean like in C. There's no indication of a mean here, although you could figure it out. But it's really just talking about the most basic element of a distribution. What is a characteristic that makes something binomial distribution? And this satisfies those criteria. For number 9, during the years 1886 to 2000, there were an average of 8.7 tropical cyclones per year, of which an average of 5.1 became hurricanes. It seems like a count of values. Assuming the probability of any cyclone becoming a hurricane is independent of what happens to any other cyclone, that's an assumption. If there are 5 cyclones in 1 year, what's the probability at least 3 become hurricanes? All right, so just going back to number 8, do we have a fixed number of trials, 5 cyclones in 1 year? Probability at least 3. They gave us some background information. They told us that on average that we would have 8.7 per year, of which 5.1 would become a hurricane. So I'll focus on the number in a second, but the probability of a hurricane, just in general, based off the numbers that we have, 5.1 over 8.7. So you could say 51 over 87. Slide the decimal over for a second. But if we have a fixed number of trials in a given year, yeah, that's where the 5 comes into play. The probability, we're looking for the probability of at least 3 of them becoming hurricanes. All right. So you could do this using the binomial formula, or you could do it on your calculator. This would be a binom CDF. Now, if I go into my probability distributions, if I can ever get there, binomial, we have binom PDF, binom CDF. PDF is for a particular probability. So if I wanted to do, let's say, probability of having exactly 3 cyclones, exactly 4, exactly 1, doesn't matter. then I would use this one. But I want the probability of getting at least, now this one gives me at most, all right? So the probability that x is greater than or equal to 3 is going to be equal to 1 minus the probability that x is less than or equal to 2. All right, because this is a discrete probability situation. This is the key value, because if it's not less than or equal to 2, then it's going to be greater than 2. The first value that's greater than 2 is 3, and then beyond that 4 or 5. So that would be the case of at least 3. All right, so if I do 1 minus binom CDF, 2, my number of trials is 5, and my probability of success, 51 out of 87, although a cyclone becoming a hurricane may not be necessarily considered a successful thing, but that's how we define it. 2, 5, and then 51 over 87, we get about 0.658. So that's D. And there we go. All right. Number 10, some more probability. Given the probabilities P of A is equal to 0.3, and P of B is equal to 0.2, what is the probability of the union if A and B are mutually exclusive? All right. And then, because they have to be who they are, they wouldn't just leave it at that. They'll say if A and B are independent, if B is a subset of A. All right. So the first thing I would do is I would look at my handy dandy formula sheet. So the probability of A union B is normally equal to probability of A plus probability of B minus the probability of A and B occurring at the same time. All right. If events are mutually exclusive, so this is the general formula. Mutually exclusive would be just this part. All right. ME for mutually exclusive. They told us 0.3 and 0.2. That gets me a 0.5. So that's the first part. So I can wipe out these choices and really just go from there. Now, it's really just kind of deciding between the last possibility. So the component where they talk about being independent, A and B are independent, actually ends up not being relevant because the two remaining choices both have a 0.44 for that. So if they're telling us that B is a subset of A, all right, so I'll just do it as a Venn diagram. So B is part of A. B is a subset of A. So this is my A. And the probability of A is 0.3. If B is part of A, just do it like that, and A amounts to 0.3, if I'm looking for the probability of the union of A and B, just remember when we do Venn diagrams, I mean, it's been a while, but when we do Venn diagrams, we shade in whatever the relevant events are. So that would be all of A. And then B, right? And what we look for in a union is any part of the graph that has any shading whatsoever, right? And so in this case, we're talking about anything that's contained within A, which amounts to 0.3. So I would go with D as my final answer, because if we're looking at the union of A and B, but B is already part of A, then we're really just looking for the probability of A.